This is the image that we ended up with last time. We were talking about rest energy. And there's a lot of misquotes here. Okay? A lot of misquotes and a lot of bad wording when it comes to rest energy. And one of the reasons why is that you'll hear people say, oh, the mass of the system increased. And we already talked about this last time. That's a problem. Mass is an invariant. And because it's an invariant, the mass is always the same for all inertial observers. So what they're really missing here is that even though they say mass increase, what they really mean is that the mass energy increased, not the mass. The mass energy increases. So that's what you really want to pay attention to. And so I said that when we talk about mass energy conversion, they just, and we're going to be talking about what we mean by binding energy as well, and the same thing here. The key point is that when you're looking at this thing, the easiest way to really see the two possible situations is that if I have matter and antimatter annihilating, well, as we said before, it can convert this mass energy into pure energy. In other words, if mass disappears, I should be careful. If mass energy disappears, then there must be energy created in some shape or form. And when you look at nuclear interactions, I mean, you could look at atomic interactions too, or even human interactions. That's a tiny, tiny amount. In nuclear reactions or particle interactions, you find that the energy that's being released or emitted is much higher. But at the same time, as soon as I have this pure energy can then create new rest energy particles. And as it does that, this shows here that pure energy can create massive particles or mass energy. And so what we want to do here is that to really, because this is a conceptual thing that's really misspoken about online in textbooks. Textbooks get it right. It's just the language issue. Layman textbooks, I think, are misleading in the language. And so I want to make sure that I try to do a good job of trying to explain what the scenario is. And the best scenario that I could think of is I want to give you a macroscopic analogy. Now, what I'm going to do here is that I'm going to imagine that I have two carts. So suppose we have two carts with attachments. So what I mean by that is that one cart they have spring. So if I was to take my cart, let's say this is my cart here. What I'm going to do here is that I'm going to come in here and I'm going to attach a spring. So if I compress the spring here, then this becomes a repulsive force between two carts if I compress the spring. Now, on the other hand, what I'm going to do next is that I can also attach Velcro to the cart. And if you were to look at the carts at Cabrillo, we have these carts that are called dynamic carts, and they actually have internal springs and they actually have Velcro in the system. So what you're seeing in this scenario here is that if I have my carts again, what I'm going to do here is that I got to sort of like draw a Velcro. How do you draw Velcro? I have no idea. But what I'm going to do is I'm going to imagine that this guy right here is my Velcro. So as we know, if I have Velcro and I put the right type of Velcro then those two Velcros are going to do what? They're going to stick with all those little tiny hooks. So this force here is going to be an attractive force. So what we want to look at is that if I put two carts together, there's going to be two interactions. There's going to be a spring interaction and there's going to be a Velcro interaction. So what I'm saying here is that there's two ways to form a bound state between two carts. And so what I imagine here is that I'm going to have the following scenario here. So if I come and I now attach these guys, so that means one has the Velcro, and I come in and I actually do what? I have this cart, I have this cart, and then when I look at my Velcro is right in here, and then my springs have now been compressed. So I look at my springs and they got compressed inside the cart here. And what you're seeing here is that there's two opposing forces now. So now what I have here is that I have a bound state with two opposing forces. In one force, I have the spring force that's actually the repulsive. They're trying to break this bond apart. On the other hand, I have what? I have an attractive force between the Velcro, and that's trying to keep the system together here. So what you're seeing here is that now I could talk about what? What I could talk about is that I could talk about where I have, if I have the repulsive force greater than the attractive force, then what you get here is you get a temporary bound state, and this is what we call unstable. I have an unstable bound state. On the other hand, if I have the attractive force greater than the repulsive, then this state can be a stable, right? This could be a stable bound state. So there's two cases to consider here. And what you're going to find here is that because I did work, let's say, in pushing these things together, people then say that, oh, I added energy to the system, and therefore the energy did what? It increased the mass of the system. That's what you hear a lot being said. And I'm saying that that's a bunch of BS. Mass is an invariant, so mass can't increase. So what increases? The mass energy state. And what relativity tells you about is it tells you the difference between the bounded mass of the system versus the constituents. So there is a difference between classical and relativity physics. In classical physics, what they have here is that they have a really strong law in classical physics. And it says that the law of conservation of mass, and it literally said that if I have a bound system, this bound system is always equal to the constituents. And what you're going to see in relativity, mass is not conserved. And what you're going to find here is that the mass of the bound system is not equal to m1 plus m2. Okay, now this is only true if I have a bound system. If I don't have a bound system, it doesn't make any sense. Okay, so now what I want to show you here is that I'm going to show you that if I have, so what this really tells me is it tells me two things. So if I have an unstable bound state, what this tells me here, excuse me, you're going to see that the mass energy of the bound system is going to be greater than the mass energy of its constituents. Relativity clearly predicts this. Whereas on the other hand, if I have a stable system, what you're going to find here is that the energy of the bound system is actually less than the mass energy of the constituents. And there are very, very strong pictures that will show you what I mean by this thing here. Okay, so let's go look at each of these two cases here. So what I'm going to do here is that I'm going to talk about case number one. And in here, I'm going to talk about unstable bound states. And in case number two, I'll talk about stable bound states. So let's go look at this thing here. So what we find here is that I imagine that I have two systems here, right? So I have my cart, which in this case, I'll draw in gray. And then I have a second cart, which I'll draw in gold. So just so that we can separate these guys out nice and clean. And so when I'm looking at these, I'm going to call this guy number one, and I'll call that guy number two. And then what do I have? I have my Velcro. Remember, the green is the Velcro. And then I have my red here. So when I look at my red, here's my springs. Now, in order for me to form a bound state, right? To form a bound state, I must do work. So that means if I look at my system now, what you're seeing here is that now I'm coming in, and what am I doing? I'm going to do work on my system. And since work is the other side of the energy coin, what you're finding here is that what am I going to do with that work? It increases the overall energy of the system. So what we're seeing here is that in order for me to get these to work, to actually do that, there's going to be an increase in energy overall. So that means that afterwards, I have a system that looks like this here. Right? I have to do work to compress the springs. So when you're looking at these guys, you're finding here that this is a higher energy system. There's no way around it. And the reason why it's a higher energy system is because now I have a compressed spring in here, right? I have a compressed spring. So my system, I'm now at a higher energy state. So where did that energy come from? It came from the work that I did, right? It came from the work that I did. So in other words, the work by my hand increased the spring potential energy, right? So my work got stored in the spring. And that's where it's getting that system here. So the question is, how does one interpret this from the mass energy viewpoint? I need to translate this thing to, the relativistic regime here. So what happens here is that what this means here is that if you increase potential energy, this means here that there must be an increase in mass energy of the system. And what we call this increase in the mass energy of the system, this implies that when I compare this sort of bound energy, which I'll write it like this, assuming that this system has zero kinetic energy, then that means that the bound energy of this thing here must be greater than the individual carts beforehand. Why? Because this guy got what? There's the work done to increase. And it turns out that it turns into this mass energy increase in the system. Now, can I differentiate between the mass of the cart and the spring? Well, the answer is no. If I can't look inside the cart and look at that spring, then all I know is that the system has a higher energy. I can't separate the spring energy from the mass energy. It's all in the same cauldron at this point. And the same thing happens when you talk about particles in nature. So if you're looking at particles, that's a composite of the system. All I know is that I look at this thing and I might look at its energy and momentum and how it interacts with other particles. I can't look inside this particle and just pull out the mass out of this thing, because now inside this bound system, these particles can have overall increases in energy, like the kinetic energy of the particles within the bound system. And that's exactly what typically happens. And so if you talk about the quarks inside of a proton or the quarks inside of the neutron, I can't separate the quark kinetic energy from the potential energy of the strong nuclear force inside of protons and neutrons. So it's mixed up. I can't separate them. And so what happens here is that now what we say here is that the only thing that we know is that in a system here, what we find here is that for unstable bound states, this implies that the particle will decay or break apart. Okay, it has to. So let's go look at this thing here. So now if I look at this thing, what do I know? Well, let's go think about particles again. So now instead of cards, I'm going to think about particles. So I have two particles. Okay, so if I have two particles, I have particle 1 and I have particle 2. And I'll color them the same because I want the same analogy to actually occur. So I got 1 and I have 2. Now, typically what you find in nuclear or particle physics type situations, you have to force these guys together. And the reason why you got to force these guys together is that they typically have the same electric charge. That's the easiest scenario. So I won't talk about strong nuclear forces or weak nuclear forces. Charge is the easiest thing. So you could imagine that I have two positive charges and I want to form a nuclei. So what do? I take these two positive charges and then I'm forcing these guys together. As I force them together, I get them so close that eventually the strong nuclear force sort of like grabs onto them and grips them, and then it forms an unstable nuclei. So you could imagine now that here's my system, and what am I doing? I'm forcing these guys together. In other words, I'm going to do work to form an unstable, let's say, a system. Maybe the system I should say here, since I started saying nuclei, would be sort of like a nucleus. So now, here I go. I now have an unstable system. So that means then, in some shape or form, these guys are now bonded together, right? They now form a bond here. And when I look at this guy here, what you're seeing is that this guy starts off with rest energies of M1 and M2. And now what I'm saying here is that now this system now has an energy that should be related, where when I look at this PC term, this term here, oops, I forgot to square this guy. This guy here is 0 because it's not moving. So when I look at the energy of this bound system, the overall energy has increased. I mean, what else am I going to have, right? Where's my work going to go? My work doesn't disappear. Conservation of energy says that that work is still there. It just got transformed into something else. So then what happens here is that because this is unstable, we then get what? It decays into products. And as it decays into products, what you're going to find here is that these guys can then shoot away, right? They're going to break apart because we already said that they're unstable. So what that means then is that not only do they have rest energies, but they now have kinetic energies in the system here. So what does this mean here? Well, it means this. So if I follow a flow chart, right, I'm going to think about a flow chart of process. We do something like this. So the flow chart says that I did what? I had to do work. And what did I do? I changed the energy of the system, right? There's a total change in the energy of the system. Now I have a bound energy system. this bound energy system must be a combination of the two constituents, where this bound here is, this has to be the mass energy. So now that I have an increase in mass energy, since the system is starting at rest, then that means that when this system now breaks apart, right, it decays. Remember, I'm still following my picture up above. So as it decays, we could see here that each of these particles must have this amount of energy afterwards. So when I look at this system, this means then that I have the rest energies of the constituents themselves, but now I have this extra term that's due to the kinetic energies of the decaying products. And so what you're seeing here is that this here is the rest energies of constituents, and this guy here is the kinetic energies of the constituents. And then this thing here is the bound, maybe I should say this is the unstable bound mass energy of the system. So when you look at this thing, you can see here is that there is a change in mass energy. So that if I just rewrite this thing, you could see that this thing is not equal to zero. It's equal to what? The kinetic energy of these constituents here. And so what they typically do here is that we say there's a change in, here, I'm going to move this over a little bit. Right? So what we say here is that there is a change, right? There is a change in the mass energy. That's what I mean by that, right? This change is that change right there.
Hey, Carlos.
Yes.
If you put the two particles that are bound on a scale, and then you just put them separately on a scale, you're saying that the two particles that are bound together would have a higher mass calculated from being on a scale. Is that correct?
Yeah. I would be careful with what you said. You are correct. I would say that when you say mass, remember mass is an invariant.
Yeah.
So
what it shouldn't change on a scale.
No, it should change on the scale. But it's not the mass that increase, it's the mass energy. And what I mean by that is that one example that I'll tell you here is that just to try to explain this, here's an analogy. But you are right, Nico. You are right. So when I look at this analogy, let's look at the proton, for example. The proton is such a sexy little animal. I can't even begin to tell you, because that proton confuses the shit out of me. What you find in the proton is that there are 3 quarks, and they appropriately call them red, green, and blue. And that has to do with the charges of them. And so if you measure the mass of the quarks inside the protons, the mass of the proton is not even nearly close to the mass of the quarks. In fact, I think the mass of the quarks compared to the mass of the proton only make up like 10% of the mass. So these quarks here are about 10% of the mass of the proton. So the question is, where's the rest of the mass? I put a proton on a scale, and on this scale, it reads 938 MeV, but you're only seeing 93.8. Oh, excuse me. Yeah, you're only seeing, is that right? Yeah. 93.8 MeV is from quarks. So where's the rest of the mass, right? And the answer is, it's in the kinetic energy of, of the quarks and these things called gluons. So even though I put the proton on a scale and it reads 938 MeV, most of it is actually kinetic energy. So do I call that mass? I say that's wrong to say. What you should say, it's mass energy. The mass energy of that system increased.
Gotcha.
You understand what I'm saying?
Yeah, so a scale measures more than just kind of what we think about as mass. A
Right.
scale would measure mass energy.
Yes. And that's why I said that textbooks, they keep saying, oh no, there's a mass increase. And I say that's bullshit. And the proton is like the most, realistic example of what that is. So this tells me about how I measure the change, and relativity clearly predicts this. This is a violation of classical physics. Classical physics will tell you that the masses are the same. Relativity shows you that because of mass to energy conversion, the mass of the bound state and its constituents is different.
So does this mean that thermodynamically this is not like the same sort of, or is it?
Well, thermodynamically, if you want to be precise, that energy scale is so small that you don't even consider it. The energy scales compared to thermal are so much bigger that you can just ignore it.
Okay.
I mean, we're literally, so if we're talking about this guy here, anything thermal. I mean, we're talking of the order of 10 to the 6th to 10 to the 8th scale difference. So we typically ignore all thermal stuff. So, I mean, even though the proton's a really good example of this, what I would like to do here is that I want to give you some hard numbers. And the example that I want to think about is I want to look at mass energy conversion in nuclear systems. And, there's a lot of great examples here. Like you could talk about the difference between a coal plant versus a nuclear plant. You could talk about what happens in nuclear bombs. Where do nuclear bombs get their energy? I mean, God, there's so much cool stuff to do in here, but I'm just going to give you a very simple example so that you could see what I mean by this mass energy conversion in the system here. And so what we know here is that there are 3 types of nuclear decays. that doesn't mean that nuclear decays can only be explained by three things. I mean, if you look at a nuclear physics book, those goddamn things are massive, and it's because they're pretty goddamn hard. And what you find here is that these radioactive nuclear decays are known as alpha, beta, gamma. And what you find here is that alpha is due to the strong nuclear force. Beta is due to the weak nuclear force. By the way, we typically don't call them forces. Forces is too simple of an expression. We actually call them interactions. Interactions is a more complete statement. And then we have a gamma decay, and this is gamma decays are due to electromagnetic force or electromagnetic interaction. And what you find here is that if you look at nuclei, you know, even though there's some really crazy nuclei on the periodic table, radioactive decay does not start really till bismuth. There are some exceptions to this thing, and you can't look at the periodic table and actually explain why something can decay. You actually have to get inside the nucleus and look at how the protons and neutrons are set up structurally. So it's more complicated, and therefore we won't get into it. So what we find here is that one type of decay that we'll look at here is that I want to look at an alpha decay. And so when you look at an alpha decay, it means that there's a parent, decays, and produces two daughters. And what we mean by a parent is that I could give you, in the example here, is that the one that I chose, just because I think it's is an easy one to look at. You look at thorium-232, and it goes to, what's it called? Damn. Radium. Yeah, it's radium-228 radium plus an alpha particle. Okay, plus an alpha particle, where an alpha particle is a stripped helium nuclei. And so in other words, if I was to look at an alpha particle, what you'll see here is that there's two protons, right? So I'm going to say there's two protons in here, and there's two neutrons. So I kind of think of this little packet, and it turns out that a helium nuclei like this is extremely stable. I mean, in fact, that's, you know, a quarter of the universe is made up of helium atoms, but it's extremely stable. And so typically heliums in complicated things like thorium actually form this very tight bound state inside of thorium, and it's actually bouncing around, but we can't even tell that. And so what you find here is that there was this amazing, God damn it, what's his name? George Gamow. I think this is how you spell it. He's this Russian guy that immigrated to the United States. This guy should have won the Nobel Prize a couple of times. There's some snakes in the world that he ended up not getting it here. So by the way, I should have said here, this is the parent, and then these guys are the daughters. And what you find here is that you could imagine what happened to the proton. So when you look at Nico's excellent question, this proton, I can't tell that the quarks are actually moving inside. The same thing happens with thorium. And so George Gamow, what he did here, he was the first to model alpha decay. And this guy is so freaking funny. He's written some really, really great books at the layman's term. And I'll talk about them later, but man, this guy is a joker without any doubt. And so here's what he said with this model here. What he did here, he says that inside of thorium, okay, I don't know how to spell thorium, so if this is close, I'm okay with that. Is a trapped alpha particle. Just like we can't look at the outside and say that there's quarks inside the proton, in thorium, what you're finding here is that I have thorium right here. Okay, so here's my thorium. And inside is that I have this little nuclei, this helium nuclei that's bouncing around. So this guy's literally going back and forth, and it's trapped. It's trapped inside thorium. And so what he did here is that what George Gamow did is that he created a model. And this model was amazingly impressive, and it still holds today. So here's the model. So what I imagine here is that I have something that looks like this. So if I was to draw a circle here, maybe it looks something like this. And what you're seeing here, that this represents the diameter of this is the diameter, not the diameter, the radius, the half sphere of thorium. Okay, and what you're finding here is that inside of here, you have this little collection of protons and neutrons, and they're bouncing inside of this thing. And as it bounces, what you find here is that what's keeping it in there? It's this thing called the strong nuclear force. So what it does here is that if I was to draw the strong nuclear force, it looks like this. The well it looks like a little well, and then it sort of like falls off like this. And so what you're seeing here is that what I'm really plotting here, you know what, I got to move this down a little bit. I drew it too close. So what you're finding here is that up here at the top, I have energy. So I'm plotting energy, and this distance here, this is the radial distance. And so what George Gamow is saying is that this guy is just bouncing back and forth. It's trapped within. So remember, this green line right here, okay, that green line is thorium. That's the potential mapping of thorium. And so what happens here, as this thing, so this is what they call, maybe I should write this a little bit better. This is what they call the potential barrier. And it's the electrical topo map, or the nuclear topo map too, of the whole thorium atom. And so eventually what happens, this guy bounces out of here. And as it bounces out of here, it's called quantum tunneling. This guy then sort of like shoots out. And this is where the alpha escapes via quantum tunneling. Now, we don't need to know the details of quantum tunneling right now. All we know is that it escapes here. So the question is, what actually happened? Well, this system is unstable. Why? Because the repulsive force, which is in this case is the electric, is greater than the attractive force, which is the strong nuclear force. And because it's right, so in other words, this is really sort of like the Velcro. What they call the strong nuclear force is they call it the glue, and then this guy represents the spring between the two cards here. And so what happens here is that eventually you have a system, and this is what ends up happening now. So I have two, oops. So picture-wise, I have what? I have a big-ass monster here, which is the radium. So I have 232 radium, and then I have a little tiny alpha particle. And when I look at this alpha particle, what am I doing? This has a positive charge. And this positive charge on this guy is, let's see, radium, that's got to be, God, I don't even know what it is on the periodic table. It has it's probably, I'd say, around 60. Its atomic number must be around 60 or so. I don't know, but it's somewhere around there. This has a positive charge, and this has a positive charge. So what I have to do here is that when I do work, right, this represents work to push them together. So when I do work to push them together, when I look at my system, what am I doing? Apparently I'm not doing this. I add energy to the system. And as I add energy to the system, I have a high energy system. And one of the most important laws of physics is that if you have a high energy system, it's always going to move towards the lowest possible energy state. So that means then what we find is that inside of this thing, you're finding that you have a combination of these two now. But now I can't tell the difference between a helium and a radio atom because now I can't see inside. This is now, I made a mistake over here. So this guy over here should have been 228, okay? I was just looking. And this guy is now 232 thorium. I can't tell the difference to them. So now when I look at my thorium, I'm assuming that the thorium is at rest. So I look at the mass of thorium and then I say, but this is at rest. You're seeing here that the work that I do here increases the energy of the system. It now goes into the mass energy of the thorium, and then at some point, what's it going to do? It's going to decay, and as it decays, then I see these guys taking off here. And so as I see these guys taking off, that means I have two kinds of energies. I have the rest energy of the radium, the rest energy of the alpha, but I also have the kinetic energy of the radium and the kinetic energy of the alpha. So when I look at this thing, here's what they find. Experimentally, what they find here is that the kinetic energies of K Oh man. Radium plus the kinetic energy of the alpha, they measure to be 4 MeV. So this is the kinetic energy that these guys actually escape from. So what does that mean? So that means here that when I look at the change in the mass energy of the system, it has to be 4 MeV, just from what we talked about a moment ago. So the thing about it, how can we check this? So the way you check this is we're going to ask how, what is the energy of the system here? And what we want to say here is that how much mass energy is this? Well, one thing that we can do here is that we could just say, well, I know that we're talking about this amount of mass energy, and this has to be what? It has to be, if I look at just the mass, then this has to be K1 plus K2, and look, I'm putting in C squared here. So if I look at this mass, then it's going to be 4 times the kinetic energy, which will be 4 times 10 to the 6 electron volts. Now I have to put in C in this case. So if I put in C, I get that. But note that this is in electron volts, and there's a conversion factor, which reads that this is 1.602 times 10 to the negative 19 joules divided by 1 electron volt. So this is just a mass energy conversion system so that I could just estimate what the mass difference is. So when I look at the mass difference, this is about 7 times 10 to the negative 30 kilograms. So this is how much, as the textbooks would say, this is how much mass loss that thorium had. Remember, I wrote this because this is very deceiving, right? I'm going to say this is a joke. Mass is an invariant. What they really mean here is when they calculate the kilograms, they really mean mass energy, even though they calculate kilograms. So what you're finding here is that, it's very deceptive. It's bad use of language. But there is some there is some light at the end of the tunnel that I'll show you here. So here I go. So what I want to do here is that to check this number, let's look at masses. So what you find here is that if I have a nuclei, and then I have the mass, what they say here is that they measure this in what are called atomic mass units, and U stands for atomic mass unit. And it's actually based off of carbon. So that's where that really comes from. And so now if I have 232 thorium, I have 228 radium, and I have my alpha particle. My alpha is a helium nuclei. So now I could come in here and I could look up the values. And this is what you find. So the sig figs are huge here, okay? Because they're tiny amounts that we're actually really talking about. So let's go look at these numbers here. So if you look up thorium, it's 232, and then it's 038051, 228, which is 031064, and then I get 4.00260. So I know that there's a lot of sig figs here, but we actually need them in this case. So when I look at this atomic mass unit, it's equal to 1.66 times 10 to the negative 27 kilograms. So here I go. So what I need to do here is that I need to subtract. Oh man. These. That means that the experimental bound value of the system should be the mass of thorium minus the mass of radium minus the mass of alpha. And when you look at this, you subtract these, you get 0.004 U. So all I'm doing is that I'm just subtracting these three. And then if I do the conversion, to 1 U, to 1 sig fig, you get 7 times 10 to the minus 30 kilograms. So so this is what relativity predicts. This is what you measure experimentally. So what you're seeing here is that they actually measure up. But remember, this is tricky. It's a mass measurement, but it's really the mass energy of the system. I'm holding thorium, but I can't tell that there's an alpha particle bouncing back and forth like this. I can't tell that there's a radium particle that's essentially stationary inside of thorium. But if I hold it in my hand, I can't tell the difference. I only know that there's a difference when it breaks apart. And so if you the same thing happens. I mean, so another example that I could think about is sort of like a nuclear bomb. So a nuclear bomb, where does it get its energy from? What you find here is that it does this. So when I look at the second bomb, no, we could talk about the first bomb. The first bomb was a 235 uranium bomb. So if I look at the mass of the bomb, I'm really looking at 235 uranium. That was the first nuclear bomb dropped by the States on Japan and Hiroshima. And when you look at the change in the nuclei, what you're finding here is that this mass energy, the bomb converted some of its mass energy into pure kinetic energy. So what you're seeing here is that let me get rid of this. So the 235 uranium atoms lost. Nope, bad word. Converted some of its mass energy into kinetic energy of its constituents. So that means I started off with 235, and after 235, what ended up happening? It broke apart. And typically what happens is that it has a heavy daughter. And then what it typically shoots out is it shoots out a stream of neutrons. And what you're finding here is that these guys have high kinetic energies. And so that's why when you see this nuclear explosion, you see this expanding piece. And the crazy thing is, a nuclear bomb is really an electrical bomb. And the reason why it's an electrical bomb is because now I have positive nuclei that are really close together. And what do? They repel each other very strongly. So you're converting part of the mass energy of the 235 into electrical kinetic energy, which then causes that with the explosion. Let's move on. So now let's look at the second case. In the second case, we want to talk about stable bound states. And one of the things that we talked about when we talk about when we talked about it before, that if F of the attractive force was greater than the repulsive force, then what this implies here, that I can form a long, stable state. So what we find here is that a stable system is the opposite of an unstable system. And what I mean by that, so if I looked at an unstable, what we found here is that what do we have to do? We do work to bring them together. Since F repulsive is greater than F attractive. So the opposite happens when you have a stable system. So what we do here is that we do work to break them apart. Since it's the opposite, because F attractive is greater than F repulsive. So it's literally the difference of this thing. Now, this is a very, how do I say, tricky thing to visualize. And really the only way to visualize this thing completely is that with a physics 4B background. And I know some of you don't have that, but I'm not even sure if you take 4B that you may have seen it this way, because 4B is about creating topo maps of what charges do. That's probably the most important thing that you should get out of physics 4B. And so what I want to do here is that I think I can draw a picture that doesn't require 4B knowledge, and it explains what do I mean by a stable system. And by the way, this is exactly what quantum mechanics tells you at the same time. So what I want to do here is that I want to talk about a bound state, and I want to create a picture. So I need to create a picture to explain this. Okay, so what we do here is that an electric potential is a sort of like a topo map or topographical mapping of electrical space. And what I mean by that, if you're riding your bike, right, you could imagine that if you're on a bike or in a car, if you see a hill, what you see is the gravitational potential of the Earth. And what dictates the gravitational potential? It's the topo map. It's the landscape. If you see a hill, if you see a valley, it tells you what you're going to do in that space when you're riding your bike. The same thing happens with an electric potential map. What it tells you is the electrical landscape that a charge will see. So what happens here is that unfortunately, potential is a electrical height parameter. So when you read the word voltage or volts, this is really the height on a potential map. So height is represented by this term called potential. So here we go. So let me see if I can draw a good picture for you. So what we want to do here is that I imagine that I'm going to form a hydrogen bond between a proton and an electron. Okay? There's a bond between them. So what I'm going to do here is that it doesn't matter whether I say an electron is bound to a proton or a proton is bound to an electron. According to Newton's third law, they have to be equal and opposite. So the picture doesn't really matter so much. But what I want to do here is that I want to start off with the mapping of an electric charge first, and then I'll go to the hydrogen. So here's what you find. So the potential map of an electron is like this. So I'm going to draw this thing, and it looks like this here. And what you find here is that this is potential, and this has units of volts or voltage. And so what this means here is that if I have an electron, and I'm imagining a picture like this, where this is my electron right here, what it does here is that it produces what is called a potential field. Remember what I mean by that. It sets up a landscape for the system. And so what I'm going to do then is check this out. The landscape looks like this. In other words, when I look at this thing, it forms a well in the system. And so this distance right here is and then right here, this will be the radial distance, which I defined as r. So what does the electron do? It does this. So note that because this is zero height, I put 0 volts. Remember, voltage is about height parameter. And if I was to come down here, let's say, this would be below, so I write that as a negative because it's below the axis there. So now, here I come. This is what the electron sets up. What does the proton do? So now I have a proton in here. So in this space, I have a proton. What does the proton see here? What it sees here is that it sees this curve right here, right? It sees this curve. So if I was to look at this thing, it sees this sort of like shape in space. Now we can't see it, right? We can't see it because we don't see an electrical space. So what happens here is that when I look at this thing, note that 0 volts is higher than minus 10 volts. So what I say here is that the proton in this case is at a higher height, maybe I should say electrical height. So then we say it has higher electrical potential energy. And what I mean by that is that if I look at this hill over here, if I have a ball on top of this hill, I then say this ball has a higher potential energy because it's high off the ground. So now what happens? As this proton becomes bounded by the electron, it's going to do what? It's going to move in this direction. And let's say that it continues to move, and right here is where it ends up. So note the proton in this state is lower in the well. So what we say here is that the proton is lower in the well. But wait a minute. If you look back at our previous situation here, if the ball then moves down here, what you're seeing here is that now this ball is at a lower gravitational potential. The same thing happens right here. If it's at a lower, the proton is lower in the well, what this implies then is that now it's at a lower electrical height, and so therefore it has a lower electrical potential. In other words, when I form a bound state, the hydrogen, which is a bound state of a proton and an electron, moves to a lower energy state. So that is when a proton forms a bound state with the electron, it moves to a lower energy state. And that's a really deep picture. That's a really, really deep picture. And, you know, these pictures are everywhere, right? I mean, one example, I didn't think about this here, but we could go look at this guy right here. So if I come in here, and all I'm going to do here is that all I did is that there's a thing recently that you may have read. It's called what? The Higgs potential. And when you look at the Higgs potential, let's look at this picture right here. What you're seeing here, this is the landscape that this Higgs potential, and then we envision what a particle does here. So look at this. That's a higher energy state than this guy. And so people calculate these shapes of these spaces to actually explain what's going on. That's the goal of physics, is to get this picture here. But the important thing now is that what do we know here? So now what we said here is that what we're looking at here is that we know that a stable state then requires work to get, doesn't require work. What we do here, we have to break the atom apart. So now come and look at this thing. According to conservation of energy, if I look at this picture here, I don't want to mess up this picture because I'm going to go to a slightly different topic. So I'm going to copy this and bring it down here just so that I don't screw people up here. So what I'm going to do here is that I'm going to do this thing here. What you're going to find here is that if I want to remove, okay, so I want to remove the proton from the electron. Work must be done. So if I do that, how much work do I got to do? Well, I got to lift it. Remember, voltage is height. So that means I have to lift the electron, let's say from negative 10 volts to 0 volts, or the proton's charge. So this represents how much work is required to remove proton. So then I could start to walk, sort of like walk through this thing here. Well, what do I know here? In the beginning, so initially, we had an electron and we had a proton. And this was my system here. So when I look at these guys, they had the mass of the electron and the mass of the proton. And then what happened? They went to a bound state. So now I can't tell the difference between the proton and the electron because it forms a bound state. So that means here that this here must be the energy of this bound system, which has to be what? The mass of the bound system, like this here. So now, if I break them apart, what you're going to find here is that then this bound system, we agree here, So when I look at this guy, what ends up happening is that this is a lower energy state. This is a higher energy state. The only way I can do that is that I look at what? The mass of the electron plus the mass of the proton. And something has to do what? Has to make this thing equal to the hydrogen bond state. And what we call this is the binding energy. So it's the binding energy that makes the difference between these two. Oh, damn, I'm out of time. Well, let me just box this. But this is really the upshot to this thing here.